In this discussion video, we will do some examples where we find areas between curves. So I first want to look at problem number 4 from worksheet 15, which says define the area bounded by y equals x to the third plus 3x squared minus 4x plus 1 and y equals 3x squared plus 1. So first, I want to have you pause the video for 4 minutes to try this question. So pause the video in 4, 3, 2, 1, pause it and try this question on your own for about 4 minutes. All right, so hopefully you did that. Hopefully you paused it and tried it for about 4 minutes. Let's talk about it. So I'm going to start by drawing a picture. So let's draw some axes. And I think the graph of y equals 3x squared plus 1 is easier because I know this is a quadratic, so its graph is going to be a parabola. And it's going to be upward facing because the leading coefficient is positive. Okay, and the 1 represents the y-intercept here. Okay, so we have this upward facing parabola. So y equals 3x squared plus 1. And I know that the 1 is the y-intercept because if you plug in 0 for x, you get that y equals 1. So for this other function, we have this cubic polynomial, this third degree polynomial. So third degree polynomials sometimes can look like this, where they just sort of snake up, but they never sort of like turn. Okay, they can also look like this, where they turn and then do that sort of thing. And of course, they could also, start up here and then go down like that. The way we know that is the fact that the leading coefficient of the cubic is positive means that when x is really, really big, the y value should be really, really big. So it's going to do something like maybe like this, or maybe one of those graphs where it turns a couple of times. Okay. So how do I figure out exactly what shape it has? So the way I'm going to do that is I'm going to first find the intersection points. The intersection points of these two curves. So to find the intersection points, let's set these y values equal. So we'll set x to the third plus 3x squared minus 4x plus 1 equal to 3x squared plus 1. And I could simplify this because the 3x squareds plus 1s are going to cancel. And I'll get x to the third minus 4x equals 0. Now I can factor out an x and get x times x squared minus 4 equals 0. And this is a difference of square, so I get x times x minus 2 times x plus 2 equals 0. And from here, I have that x is either 0, 2, or negative 2. So there's 3 points where they're going to intersect. So it's going to happen at negative 2, at 0, and at positive 2. So let me draw in those points. So what I'm going to try to do now is figure out, well, between these intersection points and on the outsides of the intersection points, which of these functions is going to be bigger? And to do that, I'm going to use a number line. So I'm going to use a number line, and I'll plot these intersection points, the negative 2, the 0, and the 2 on it, and I'll keep one row for the parabola function, 3x squared plus 1, and one row for the cubic, x to the third plus 3x squared minus 4x plus 1. And I'll separate out some columns, and I'll separate out a row. And I'll pick a test point in each region now. So maybe I'll do negative 3 over here, maybe I'll do negative 1 over here, maybe positive 1, and then positive 3. So I've gone ahead and plugged these in ahead of time. And for 3x squared plus 1, when I plug these in, I get 28, 4, 4, and 28. Okay. And then with this cubic, we end up getting 13, 7, 1, and 43. Okay, so with this cubic function, when you plug in a number like negative 3, the parabola is higher, it's giving me a bigger output than the cubic is. Okay, so at negative 3 might be somewhere here. The parabola needs to be higher than where the cubic is. So maybe the cubic is somewhere here. Okay, and then it's going to go up. It's going to have that intersection point. Okay, and then in between where x is negative 2 and where x is 0, the cubic has a bigger output. So at a value like a negative 1, the cubic is going to have a bigger output. And then they intersect at this point. and then x equals 1, the cubic is going to have a smaller output. So at 1, the cubic is going to have a smaller value. Okay, and then it's going to go up and have this intersection point, and then a value like x equals 3, the cubic has a bigger output. So it'll be higher than the parabola. Okay, so at this point I have a rough idea of the picture. Maybe it's something like this. But the most important thing that I care about is, what does the region look like where, that these curves are bounding? So I see there's one sort of section here, there's one section over here. And from this I can tell what my top function looks like and what the bottom function looks like, because the top and the bottom function are going to switch at x equals 0. Okay, so this is my cubic graph, by the way, x to the third plus 3x squared minus 4x plus 1. So let's go ahead and set up our integral for the area. So our area, we'll need two integrals here. We got to split it up into pieces. The first is going to go from -2 to 0. And on that interval, the top function is the cubic. So it's x to the third plus 3x squared minus 4x plus 1. And then I got to subtract. I got to subtract the bottom function, which is the parabola, 3x squared plus 1 dx. And then plus my second integral will go from 0 to 2. And there the top function is the parabola equation. So it's 3x squared plus 1. And I'm going to subtract the bottom function. And the bottom function is going to be the cubic. X to the third plus 3x squared minus 4x plus 1. Close that parentheses and dx. Okay, so from here, it's just a matter of simplifying, computing some antiderivatives, and plugging in. Okay, so that part shouldn't be too bad. I'm going to leave this for you. And I'll just say that once you work this out, at the end, our final answer ends up being 8. All right, let's look at another example. So this one wants me to find the area bounded by one continuous period of y equals tangent x and y equals 2 sine x. First, pause the video for 4 minutes to try this. 4, 3, 2, 1, pause it and try it for 4 minutes. All right, so hopefully you did that, but let's talk about it together now. So I'm going to start with a picture again. So let's draw some axes. So if I draw the graph of tangent, tangent kind of snakes upwards like this. And it has these vertical asymptotes here. One over here as well. So those vertical asymptotes occur at positive pi over 2 and negative pi over 2. And of course, the graph of tangent continues in this way. It keeps repeating like this. But because the question just says, well, find the area bounded by one continuous period, I'm just going to draw one period of this tangent x graph. All right, so next let's graph. So by the way, this is the graph of y equals tangent x. Okay, so the graph of 2 sine x. It looks like the graph of sine x, but the 2 just scales the y values by a factor of 2. So it doubles the y values. Okay, so at pi over 2, the sine x graph has its max. So 2 sine x will also have a max. It'll just be twice as high. So the graph of 2 sine x does something like this. And then it would go down and that sort of thing. And then in this direction, it would go down and it would have its min somewhere here. And then do this sort of thing. Okay, so the graph of tangent will, cross here. It intersects up here somewhere. So we are after this area as well as this area. This is the region that's bounded by these curves within one continuous period. Okay, so by the symmetry of the picture, ooh, no, that's not how you spell it. By symmetry, that area I can find by just doing the area from 0 to pi over 2. Ooh, whoops, sorry. I actually don't know that it's pi over 2. Let me put a box because I will need to figure out, well, where is this intersection point? So I'll need to solve for that. So I can find the integral from 0 to whatever that intersection point is of the top function. So the top function that I have here is 2 sine x, and then minus the bottom function. The bottom function is tangent x dx. But that would just give me 1/2 of the area by symmetry. So I'm going to need to double this. I'll multiply the whole thing by 2. Okay, so next let's find the intersection points. Okay, but make sure you see why we are putting the 2 there. It's because this region over here in the first quadrant has the exact same area due to symmetry as this region in quadrant 3. All right, so to find the intersection points, I know what y equals for both of them. Let's set those y's equal. So we'll get tangent x equals 2 sine x. And if I rewrite tangent as sine over cosine, we get sine x over cosine x equals 2 sine x. And then I could multiply both sides by cosine to get sine x equals 2 sine x times cosine x. And now I can move all the terms to one side and factor. So I'll get 0 equals 2 sine x cosine x minus sine x. And now we could factor to get 0 equals, let's factor out the sine. And then we're left with 2 cosine x minus 1. And from here, either sine x is going to be equal to 0 or the cosine x is going to be equal to 1/2. So on our interval that we're looking at, on our interval, x is in between negative pi over 2 and positive pi over 2. It can't be equal to those numbers because tangent is undefined at those values. Okay, so on that interval, sine is equal to 0 only when x is 0. And cosine of x is going to be equal to 1/2 at 2 places. This happens when x is negative pi over 3 and positive pi over 3. So in the picture, positive pi over 3 is here. And negative pi over 3 corresponds to this other intersection point on this side where x is negative pi over 3. So we now know what number to put in this box that goes as this upper limit of integration. All right, so let's plug into our area formula. So this implies area equals 2 times the integral from 0 to pi over 3, that was our intersection point, 2 sine x minus tangent of x dx. Okay, so I can handle the antiderivative of 2 sine x more easily than the antiderivative of tangent. So I'm going to split this up into pieces. I'll do 2 times the integral from 0 to pi over 3, 2 sine x, and I'll handle that, dx. And then minus the integral from 0 to pi over 3 of tangent x dx. Let's close that bracket. Okay, so for this first antiderivative, this antiderivative is going to be negative 2 cosine of x, and then I'd have to plug in the 0 and the pi over 3. For the tangent, so we've seen this one a couple times now, but tangent I could rewrite as sine x over cosine x. And from there, we do a u sub. So we would do a u sub. So from here, it's just a matter of doing these antiderivatives, plugging in and subtracting. Okay, so that part I am going to leave as an exercise for you. All right, and I'll just tell you what you should get at the end. You'll end up with 2 parentheses, 1 minus ln of 2. And that is our answer. That'll be our area. All right, so I want to do one final example in this video. Finding the area bounded by the curves x equals y squared and 2x plus 3y minus 9 equals 0. First, give yourself 4 minutes to try this. Pause the video in 4, 3, 2, 1. Pause it and try it for 4 minutes. All right, so hopefully you did that. Let's talk about it together. So I am again going to start with a picture. So I'm going to draw some axes. X equals y squared is a sideways parabola. Okay, and I know that this x-intercept is going to be right here at 0, 0, because if you let the y value be 0, x is 0. All right, and with this other equation, I know it's an equation of a line, but we can, to get a feel for it, let's isolate the y. So that would give me 3y equals negative 2x plus 9. And then if I divide by 3, we would get y equals negative 2/3 x, and then plus 3. Okay, so from this I can see that the y-intercept is something positive, and the slope is negative. So my line is going to look something like this. All right, so that is going to be our line. So one thing I'll need to know is, well, where are these intersection points? Okay, and I can see that this is the region that we're trying to find the area of. So would it be better to do a dx integral or a dy integral for this? Well, for this region, if I were to do a dx integral, and I think about a top function minus a bottom function, the top function would switch at this intersection point, because to the left of it, the top function would be this parabola, but to the right of it, the top function would be the line. Whereas if I did it the other way, and I thought about as a dy integral, and I thought about the right function and the left function, if I do any horizontal line here, whether I do it down there or somewhere higher, the right function is always on this line, and the left function is always on the parabola. So that's going to be more efficient. All right, so before I get there, let's find those intersection points, because those are going to tell me my limits of integration. So for this one, because I know x equals y squared for one of my equations, I'm going to plug this in for the x in the other equation. So instead of writing 2 times x, I'm going to plug in the y squared for the x. It's 2y squared plus 3y minus 9 equals 0. And now this will factor. So this factors is 2y and a y here. I'll get a 3 and a 3. This is positive, this is negative. So I get y equals 3 halves and negative 3. So for each of these y's, let's figure out the x value. So for y equals 3 halves, if I plug it into my parabola equation, we get x equals 3 halves squared, which is 9 over 4. And the other y value is y equals negative 3. For that one, I get x equals negative 3 being squared, which is 9. So if we label these intersection points, this one up here is when the x value is positive, 9/4, and the y value is positive, 3 halves. This one down here is where the y value is negative. It's going to be negative 3, but the x value is positive. It's 9. All right, so now let's set up our integral for area. We'll get the area. Okay, the general formula is I go from c to d of x sub right, my right function, minus x sub left, dy. So now let's plug in for what our right function and our left function are. Okay, the c and d represent sort of the smallest y gets in this region and the biggest it gets. So the smallest it gets is negative 3 for y. The biggest it gets is 3 halves. So the right function is the equation of that line. But in the equation of the line, I need to know what x is. So I'm going to need to isolate the x here. So if we isolate x, we get 2x equals negative 3y plus 9. And if I divide by 2, we get x equals negative 3 halves y plus 9 halves. All right, and now if we plug that in for x right, we'll get negative 3 halves y plus 9 halves. And then I need minus x sub left. So x sub left is from my parabola equation and what the x equals. And it just equals y squared. So I get minus y squared dy. From here, it's just an easy antiderivative. I plug in and I evaluate. So this will be equal to, I'm going to leave those details for you and tell you that the final answer will be 243 over 16.